Welcome to this explainer. Today, we're going to dive into literally the most fundamental tension in all of machine learning. It's a concept that pretty much plagues every data scientist, statistician, and algorithmic researcher out there. We're talking about the Goldilocks dilemma. It's that constant, delicate tug of war between a model being too simple, being way too complex, and trying to find that elusive state of being, well, just right. If you want to build algorithms that actually work outside of a highly controlled environment, this is the one concept you absolutely have to master. It's a story every single machine learning practitioner knows all too well. You build a model, you feed it your training data, and the error rate drops beautifully. It looks like an absolute slam dunk in the lab. So you deploy it, feeling completely confident, only for it to just completely crash and burn when it's exposed to real-world data. Why does this happen? Why does a model that seems to have learned perfectly suddenly behave like it hasn't learned a thing? The answer boils down to one crucial concept: generalization. The true goal of any machine learning model is not to just perfectly memorize the past, it's to successfully predict the future. Think about it. When we train a model, we aren't doing it just to understand the data we already have in front of us. We're doing it to make inferences about data we haven't even seen yet. If your model acts like a student who merely memorized the exact answers to a practice test without actually understanding the underlying subject, there is no way they're passing the final exam. All right, let's start with section 1, the machine learning dilemma. To really unpack this dilemma, we have to recognize that whenever we look at a dataset, we have to assume it's made up of two distinct things: the true underlying signal, which is the real pattern we actually want to learn, and random noise. That noise could be measurement errors, unobserved factors, or just natural random fluctuations. As a model builder, you're constantly walking a tightrope. You're trying to build a model that has enough complexity to learn that real underlying signal, but is simple enough to ignore all that random noise. That brings us to section 2, underfitting, or missing the signal entirely. Underfitting happens when your model simply doesn't have the capacity or the flexibility to see the patterns right in front of it. Think of this as trying to fit a rigid, totally straight line through data that actually moves in a complex, fluctuating wave. The model just cannot see the true pattern because it is mathematically constrained. We see this when our model class isn't rich enough, like trying to use linear regression to model a highly nonlinear relationship. It's going to perform poorly on the training data and equally poorly on any new data. In statistical terms, this underfitting leads to what we call high bias. Bias is basically the systematic error in your model. If you use an overly simplified model, it's going to be systematically off target. Imagine a model predicting someone's age from a picture, and it consistently overestimates everyone's age by exactly 10 years, because its rules are just too rigid. That is a highly biased model. It's making strong, completely incorrect assumptions about the data. But swinging to the opposite extreme leads to a much more seductive trap.
Let's look at section 3, overfitting, which is all about chasing the noise. Overfitting is what happens when a model fits the training data too well. If you give a model immense capacity, like a massive, heavily parameterized neural network, and you don't constrain it, it won't just learn the underlying signal. It's going to memorize the coincidental regularities. It will literally learn the noise. The model uses all of its modeling power to force the training error down to zero. And in doing so, it creates these overly complex, jagged decision surfaces that perfectly map the training set, but look like absolute chaos when you apply them to anything else. We call this phenomenon high variance. Variance measures how much your model's predictions would change if you trained it on a slightly different dataset. An overfitted model has massive variance because it's hypersensitive. If you slightly change the training data it learns from, the model's predictions will swing wildly. It hasn't learned the actual rules of the game at all. It's just hyper-specialized in the exact hand of cards it was dealt during training.
Which leads us to section 4, the bias-variance trade-offs. This brings us to the ultimate balancing act. You are effectively trapped in a fundamental statistical trade-off. If you want to decrease your bias by adding more parameters and complexity to your model, your variance naturally goes up, which increases your risk of overfitting. But if you try to decrease variance by making the model simpler and more rigid, well, your bias goes up, pushing you right back toward underfitting. The overall expected error of your model is actually the sum of the squared bias, the variance, and the unavoidable background noise. You can't eliminate both bias and variance, you just have to balance them. And this curve brilliantly illustrates that exact trap. Notice the interplay between the two lines here. The blue line represents the error on your training data. See how as the model complexity increases on the x-axis, the training error just keeps going down? But look at the orange line. That's the error on the unseen test set. It drops initially as the model learns the real signal, but eventually it hits a minimum and then just spikes back up. That U-shape is the defining signature of the machine learning dilemma. That massive gap that opens up on the right side between the blue and orange lines, that is the literal visual representation of overfitting. So let's wrap this up with Section 5, finding the sweet spot. How do we actually navigate this trade-off and find that elusive, just right fit? In Bayesian inference, we can look at this through the lens of Occam's razor. The philosophical principle that the simplest explanation is usually the best one. As we can see here, a model that is too simple, like the green line, restricts its predictions to a very narrow range, but often misses the actual data entirely. A model that is too complex, the blue line, can theoretically generate any dataset, meaning its probability is spread incredibly thin, making it super unlikely to generate your specific data randomly. The red just right curve is complex enough to capture the data, but simple enough that it doesn't spread its probability mass too thin. It naturally penalizes unnecessary complexity. This leads to a truly fantastic insight from the financial machine learning literature. Theory and model parameters are substitutes. What does that actually mean for us? It means that the more structure or economic theory you can impose on your model, the fewer parameters you need to estimate. By bringing your own structural knowledge to the problem, you inherently protect your model from noise. An oversimplified model filters out the signal, sure, but a model guided by strong underlying theory acts as a natural noise filter. It allows you to learn safely, even in highly complex, data-rich, low-signal environments.
Now, in practice, since we can't always rely on perfect theory, we use some clever algorithmic guardrails for capacity control. We use regularization, like L1 lasso or L2 ridge, which mathematically penalizes a model for having weights that are too large, basically forcing it to favor simpler representations. Or we might use k-fold cross-validation to partition our data and simulate unseen test sets, ensuring our model isn't just memorizing. For really complex neural networks, we rely on early stopping, literally halting the training process before the network even has a chance to start memorizing the random noise. And, of course, we restrict the model architecture itself, making sure we don't use a massive neural network when a simple linear model would do the job.
As we close out this explainer, I want to leave you with a bit of a provocative thought. We've seen that blindly throwing highly complex models at data inevitably leads right into the trap of high variance and overfitting. But we've also seen that theory and complexity are substitutes. So take a look at your own machine learning projects. Are you relying entirely on the algorithm to just magically find patterns in the noise? Or are you imposing enough structure and theory to actually guide it to the truth? Finding that sweet spot? That is the true art of machine learning.